Good morning, everyone. How are you all doing? Good, good. A lot of happy faces in the room. Love to see it. I myself am very happy to be here, talking to you all today. First off, I just want to give a huge shout out to Cam, Lisa, everyone who's made this happen today, bringing us all together to learn, to network, and most importantly, to have a great time. So, huge round of applause, please, for everyone. Actually, this is my first time in Sydney, if you can believe that. I've been in Australia for 8 years now, and I've finally come around to seeing this beautiful city. I guess they say it's better late than never. As I said, it's a beautiful city, and I can just feel the raw talent in this room. Just looking at me, I can feel it. Awesome to be here. So the first thing I'd like to do is just tell you a little bit about myself. So I started off my career as a Java developer, actually, in the Middle East region, or Middle East and North Africa. And then that was before I switched over to the dark side. And throughout that whole time, I noticed that there was always a gap in quality in the software world. And that was something that really bugged me. And I wanted to make a change there. So that's why I find myself now as part of the quality engineering leadership team at Deloitte. Now some of you might be wondering, isn't Deloitte an accounting firm? And while that is true, we do have quite an extensive engineering arm, so covering all things engineering, and that includes quality engineering or testing as well. So I'm really excited to share some of the cool work we've been doing with some of our clients. Away we go. Just keep that in mind. That's what a successful rocket launch looks like. We'll be touching on a not so successful one shortly. So today's talk, I'd like to talk about digital twins, what they are, how they work, why we can benefit from them. Just by show of hands in the room, how many people are familiar with the concept of a digital twin? Okay, I can see a few hands. All right. We'll be covering the basics and also giving you just an introduction to what digital twins are. So yeah, not to worry over there. So what is a digital twin when we want to define it? Essentially it's something, it's a virtual replica or a copy of something that exists in the real world. So that could be an object, it could be a system, it could be a person. And why it's so cool is that it allows us to test things, run what-if scenarios against things without actually impacting the real life thing that we're testing. Other reasons why it's cool, saves us time and money. So this is especially true with any manufacturing or design companies where they build prototypes. So rather than spending that time and cost building a prototype to then test it, be able to do so in a virtual manner and save that time and money as well. Another one that's related is preventing disasters. So if you're able to run extreme scenarios, you're able to see what the impact is on the system and then proactively address that issue before it becomes a problem. And then lastly, boosting efficiency. So even if things are running smoothly, there's always a room for improvement, right? Especially in the case for car racing, as that's an example I like. So if you're able to shave off a few seconds off the race, that could be the difference between winning or losing. So that's always something cool to see. And this is something that I'm quite passionate about. I've gone down the rabbit hole quite a bit with digital twins, so much so that I've created one of myself. If this can work. There we go. So there's my digital twin for today. That's why I suited up. So I could let him continue, but I promised Cam that the real Tarek was going to speak today, so I won't do that. So with any technology that I like to cover, I like to look at not only the benefits or solutions it can bring to current problems and future problems, but I also like to reflect back on any historical failures and see where that technology would have helped prevent such disasters. So one of those disasters is the NASA Mariner 1 rocket. So this was in 1962. I can't say I remember it. But essentially what happened was, when translating the guidance equations from mathematical to software code, they missed out a single character. And that's unfortunate, because that single character caused the rocket, to have to be destroyed 4 minutes in, never actually made it into space, and that was a waste of $18.5 million US dollars. But you're talking 1962 money, which is very different to today's money, and that would be equivalent to around $200 million. Another such catastrophe is the US stock market crash. Now, how many of you have heard of that or remember that? All right, quite a few people. So what happened there was, they rolled out software with a bug that made it use the best trading strategy you can think of, which is to buy high and sell low. So what happened was, as soon as the stock market opened up, they rolled out the software and ended up buying, $7 billion worth of shares within just the first hour. And then there was all kinds of chaos trying to bring things together, and that resulted in over $400 million lost. And then the company also almost went bankrupt. So digital twins, this is something that we've seen a bit of a focus shift onto. So as companies face more and more complex problems, they're trying to look at new technologies to help address those issues. So originally, digital twins were built on underlying technology that actually existed decades ago. So ever since the mid-20th century, really. So as the meme goes, modern problems require modern solutions, and I believe that digital twins are a part of that suite of solutions. Another interesting milestone is the McLaren digital twin development. So they were the first to introduce such a system in their industry, Formula One racing, and that was 22 years ago. So you can just imagine how much more development has gone into these kinds of technologies. And especially paired with how accessible processors are nowadays in terms of cost. You've got cloud computing, edge computing. It's just bringing a lot more availability to all kinds of industries, to come up with their own applications. So looking into the future, we know that digitization, or Industry 4.0 as we call it, we're seeing a lot of lines blurring between the physical and the digital realm, because everything is so connected. And that, compounded with, the market for digital twins, expecting to reach 35 billions by, next year, with a 40%, compound annual growth rate, which is pretty high up there. It's truly an exciting time to focus on, these kinds of systems. So digital twins are evolving. So as we mentioned, started off in the mid-20th century just as research in academia, and now I have more of an extended timeline here. I won't cover all of these points, but just as a general idea, we started off from very elementary computer-driven simulations, where only specific or niche experts could use them. And then as hardware became more and more available and simulations became more sophisticated, we saw more applications being rolled out across different industries. So some key milestones here. We've got Greaves's concept. So Michael Greaves, who many consider is the father or founding father of digital twins as we know them today. And around that same time, again, McLaren was when they developed their first digital twin solution in the industry. So from 2000 onwards, we saw that shift to incorporating simulations at the core of system design rather than, an after the fact. And now we've reached the point where, we're doing some insanely amazing things. Like a company has built a library of realistic heart simulations. And then we talk about conversational AI, where we have human digital twins, and then, your responses are personalized according to your interests. So we also have enterprise experience. So this is tracking, a product's life cycle end to end, including customer interactions. So just the sheer amount of information that goes into these models is kind of mind-blowing to me. All right, so the enabling technologies behind digital twins, I like to break up into 5 parts. So first is the meat of it, so the modeling. You've got your simulations, your model algorithms, visualization, etc. And then you've got the physical aspect, where you have all of your sensors, how you measure the readings, and what kind of materials you're using, what kind of hardware you're working with. And then you've got the data, so that's really what it relies heavily on. So for example, how do you collect it, how do you transmit it, process it, and store it? And then services, that's going to be your application layer, software, your algorithm, your architecture, etc. And then lastly, the connection, so how we connect the digital to the real world, whether it's through internet interfaces, custom interfaces, and making sure that they're secure as well. All right, so when we talk about non-determinism, basically what that means is there are external factors to a system that we're not able to predict. So things like weather conditions, traffic conditions, etc. Or even human interactions, right? So even when we talk about conversational AI, it's difficult to know what the person is going to respond with. Since we're all human, we have our own ideas and thoughts and actions. So really, when we talk about replicating that into a digital twin solution, you want to include all of those factors into it. And that's where you try to capture that complexity, because we're essentially trying to predict the unpredictable by including all the factors that make things unpredictable in the real world, if you can wrap your head around that one. Another thing that helps is improving system reliability. So if we're able to factor in all of these variables that could affect the outcome, we're better able to address them and mitigate any issues that could come out of it. Similarly, risk assessment and planning. So as an example, I like to use infrastructure planning, city planning. If you're able to factor in things like traffic conditions, environmental factors, it'll really help you mitigate any risks associated with doing any development there. Another one is enhancing decision making, and this is where it's important for the digital twin model to reflect the real world as accurately as possible. Otherwise, your decisions are not going to be based on anything solid, right? So things like, for example, if you're talking about a manufacturing plant, if you want to simulate that, you want to take things into account such as the raw materials. So is the quantity and the quality as we expect? Are the machines operating as efficiently as possible? Things like this, we can run simulations against and then see how it performs. What's the productivity, loss in that case, and then address the problem early on, be proactive about it. So as I mentioned, being proactive, so that's enabling that adaptive response. So the digital twin solution should be able to respond no matter what happens, as in terms of external factors that you've built into it. We don't want it to just crash and tell you, sorry, I don't know what to do here. It's basically designed to handle such cases and, adapt to it. All right, so why is it important to test digital twins? We know testing is important, there's no doubt about that. But like any other standard solution, first of all, you want to identify any issues. So you want to, find any bugs, get those fixed up before they affect the system in production or the real world, if you're trying to implement things in the real world. Another one is validating system performance. So a lot of these systems are very reliant on responsiveness. So if you're making real-time decisions, you want that data coming in as quickly as possible to make the right choice at the right time. And that's why it's very important to make sure that the system is performant and responds as quickly as we want it to. Another one is optimizing user experience. So as we mentioned, there's a vast amount of data coming through, and that could overload the users as well, right? Because if you're just bombarding them with all kinds of info, they're not going to be able to really use that to their advantage. And that's why it's important to also optimize the user experience, simplify things, make it easy for them to use the system. Another one is ensuring accuracy and reliability. So as we mentioned, the decisions or the digital twin model is only as good as how accurate it is in terms of reflecting the real world. So making sure that it does that makes a whole world of difference. Another one could probably group up risks and compliance as well. So mitigating risks, running those what-if scenarios, negative scenarios, seeing what happens, and then making sure that the system can handle it gracefully rather than crashing and burning. And then complying with regulations. There's actually quite a few regulations out there, similar to IoT devices, with digital twins, making sure that they're handling data correctly, securely. They don't end up in the wrong hands. So that's something that we can also, as testers, make sure that we comply with those standards and regulations. All right, so we covered just a few fields where we've seen digital twins. These are some of the more common ones. So you've got things like aerospace, healthcare, manufacturing, electricity, and agriculture. There's many more nowadays. You've got all kinds of applications popping up. But I'd like to cover two examples where we have used digital twin solutions to solve a problem. So the first one is, addressing things in the sky. So with airplanes, there was a need to balance ground and air delay, not only to save costs, but also to improve the passenger's experience. I'm sure we've all been there. You've had a flight canceled, delayed, and there's a lot that goes into that to make sure that it's the right balance between the two, depending on capacity and demand. So the solution they used there was digital twin simulations. So they're able to model the airspace in Australia and then kind of forecast, what the events of the next day would look like, and then better plan, in terms of capacity, resources to handle that load. So they used machine learning and simulation modeling to predict scenarios, and then based on the most realistic scenario, they would, go with that and put that plan forward for the next day's consoles and traffic controllers to follow. And this was all done in quite a user-friendly interface. So as I mentioned, there's so much information coming in. They want to be able to read it quickly and make decisions quickly in a simplified manner. Another one, we come back down to the ground. So optimizing the race. We talked about Formula One racing, and a big problem they had was they wanted to improve their racing strategy, whether it was in the prototypes they're building or in the team strategy they take, during the race, and to do it in a cost-effectively manner. So what they did was they also implemented a digital twin solution, and keeping in mind that each one of these cars has about 200 sensors sending live data feeds with telemetry readings. So you can imagine just how much data is coming through. You can get up to 3 terabytes of data over a course of a race. And that's tremendous if you're trying to make real-time decisions based on really quick analytics. All right, so what I'd like to talk about now is some of the unique challenges we face, when testing these kinds of systems. The first one being, trying to replicate the complexity that exists in the real world. So because there are so many factors in there, we need to be extra thorough with our scenarios. We can't cut down, because of time constraints or budget constraints. This is something that's critical, especially for digital twin solutions. Another challenge is just how many different technologies integrate to produce such a system. So we talked about all of your IoT devices, your connections, your data feeds. Maybe you have multiple platforms aggregating all of that together for your analytics to inform decisions. So just thinking about how to test all of those connections seamlessly working together, it can be quite challenging. Another one, as we mentioned, data is at the heart of a digital twin. Without that, it cannot really function and give you the recommendations you're looking for. So that's why it's important to verify and validate the data you're using. You need to make sure that it's of high quality, representative of the set of data that you're, of the scenarios that you're trying to accomplish and test. Another one is non-deterministic behavior. So we talked about how systems such as digital twins are very random in their outputs. So it's not like, for example, logging in you expect, once you click the login button to be taken to some kind of page or screen. This is like saying, if you log in, you click the login button and it closes your browser, right? It's not something that you can predict or expect. And that's where it becomes a bit more complicated. But I believe that us as quality engineers and testers are, I guess, best suited for these challenges because we're able to tackle those and think of those negative scenarios and edge cases where something could unexpectedly happen. And then we could ask the question as to how do we want to respond to such a thing. So we talked about performance and how the system needs to be very responsive, very fast, and then that's where performance testing plays a huge part. So similar to the way we do our load testing, you want to make sure that you're giving it a realistic workload and make sure that the system can actually handle it and produce the results in a timely manner. And lastly, security and privacy. So as with any other system, you want to make sure that the data you're putting through is safe, secure. Mask it if it contains any personal or sensitive information. And then privacy as well. You've got so much regulation around that, making sure that data isn't personally identifiable, etc. One actually bonus challenge I would add there, based on my personal experience, is lack of specifications or requirements when it comes to the simulation models themselves. And what happens is you end up testing a black box. Like, you're not sure how this simulation is actually running. You just know that it's supposed to produce results in this kind of range. And I think it's very important to address that early on, make sure that we are documenting how the simulation model works, to make sure that it actually does what it's supposed to. Now that we've covered the challenges, I'd like to say a bit about the testing techniques that you could use to address those issues. So first of all, you need to know where you're going, right? So to do that, you need to define your objectives. So what are you trying to achieve or accomplish from building this digital twin? Are you trying to improve your race time? Are you trying to build prototypes more cost effectively, etc.? So outlining all of those benefits that you'd like to see is the first step. And then any risks that you see arising to also be noted with a mitigation plan in place. And then the last one, which is quite important, is how are you going to constantly monitor and compare the real world with your digital twin to make sure that it actually is following an accurate representation. The second thing to do is to make sure that your data, as we mentioned, it's the backbone of the system, so you need to make sure that the data is clean, of the right quantity, it's a representative set that covers a wide range of scenarios, and that it's in the correct structure that you expect. So it's very critical for us when testing to make sure that we do some extensive data validation. The third one is verification and validation. So this is kind of a two-step process, but essentially it's to make sure that the model behaves as expected. And this is, as we mentioned, considering or assuming that you do have requirements and specs that are quite clear in terms of how the model should operate. So the first aspect to it is verification, which is actually checking the model itself in terms of logic, functionality, structure, and architecture. And then the second part is validation. So once you make sure that your model is performing as it should, based according to specs, the next step is to make sure that it actually follows, real-world events and real conditions. And this could also be improved over time with the help of things like machine learning. So if you think, things don't go according to plan, the system should train itself to be able to recognize these patterns and produce a more accurate prediction. And lastly is the sensitivity and uncertainty. So when we talk about sensitivity, it's kind of like turning a knob or pulling a lever and then seeing by just how much your output or prediction changes by. And this allows you to basically categorize what are the most influential factors in your digital twin model, so that you're able to know which is the most impactful based on how little you change those variables. And then when we talked about uncertainty, so no matter what, there will always be a level of uncertainty because we're dealing with randomness and random variables. But what this allows us to do is find out what is the range of error that our system has. So if we're saying, it could be plus or minus, 5%, it could be even more. So it's important to categorize that and identify that in order to see how well the model is performing against the real world. Now I'll add on just a couple more techniques, again based on the last challenge, which was the lack of specs or requirements. So what we had to do in some cases is employ some quite elementary checks for regression testing. So things like, for example, if we pull lever A and we expect the output to go down, we would have checks in place or tests in place to see if we do pull that lever and the number goes up, for example, instead of down, then that gets raised as a potential bug to be looked at. Another way to do it is also to track against the baseline simulation. So for the same set of inputs, you keep running that simulation with every release and change to the model, and then see how the output changes from release to release to see if there's a huge shift in that performance. What I'd like to do now is just look a little bit into a crystal ball and then see how digital twins might evolve and where things could go in the near future. So I might get a lot of hate for this one, but I do see autonomous testing, to some degree being possible in the near future. We already see, a bunch of tools being able to, with the help of AI, automate, generation of test cases based on specs, generate the test code for you as well. So we could reach a point where, you just give it the requirements and the application that you're dealing with, and it could just go and do some, at least sanity testing as a basis. But I do think that there will always be room for us, to kind of inform that analysis and see what actually, the negative scenarios, the edge cases that AI could, might not really think of. Another one is a personal favorite of mine, and that's personalized education. So what I would like to see with human digital twins is to actually personalize the educational program. So rather than rolling out a generic program across a whole class, it would be more tailored or suited to their strengths and weaknesses, their interests, just to give them that motivation and actually want to learn. Another one is AR integration. So I believe we do have some of that currently. So, in terms of designing any models, you're able to do that through AR to then create that prototype in a digital realm before you actually produce it in the real world. And lastly, which is something I'm also excited about, is advanced healthcare diagnostics. So we talked about how we have human heart simulations running. What I would like to see is a personalized anatomy of every patient, because everybody is different. And I think that would allow doctors, surgeons to run those simulations as well. What if scenarios? See what would work for that patient, what would not work for that patient, and hopefully save a lot of lives that way. Another thing I like to do when looking at future trends is the Google search trend. So in this case, I've looked up digital twin for the last 5 years at a global scale. And you can see it's just been increasing. And I think it's an exciting time for us to look at that. So just to recap to what we've covered. So we talked about what a digital twin is, what it does, how it behaves, and why it's important. We also talked about the non-determinism or the randomness and variability in such solutions. We also talked about why it's important to test them, some of the unique challenges we face when testing such kind of solutions, and then some techniques or strategies to use to address those problems and make testing a lot easier and streamlined. And lastly, we just talked about some future directions in terms of where I see digital twins going, their integration with AI and AR. So I think now we can move to the bonus question, or the gift card question. So which Formula One company pioneered digital twin technology? I saw the first hand right there. McLaren, that's right. Oh, yeah. Congratulations. Should probably show that as well. There we go. Yeah, thank you so much for listening, everyone. Hope you have an amazing day. And if you have any questions, please feel free to come to the Meet the Speakers booth. I'll be there from 10:30. So, yeah, keen to bounce off ideas with anyone who's interested. And if you have any recommendations while I'm in Sydney as well, yeah, please drop by and let me know. Thank you so much.